Thank you, everyone, for attending, and thanks for the invitation. I'm going to follow Thankful's outstanding talk, as well as the ones we saw yesterday, by discussing what we can learn about dense matter from NICER observations. My general plan here is going to be to talk about our results and how we obtained them for the two pulsars for which we have published results, radius, but also mass in one case. And then I'm going to discuss some of the implications that this has for the equation of state of the matter in neutron star cores. As we heard from Serena yesterday, there are two separate groups within NICER that are doing this analysis. I'm going to focus on the results of our group, but I definitely encourage you to look at the results obtained by the Amsterdam group, especially the Riley et al. Papers from 2019 and 21. We also, in this conference, have a number of other presentations that are relevant to dense matter from neutron star observations. We heard two yesterday from Serena and Jocelyn. We just heard from Thankful. And after my talk and the break, we're going to hear from Slavko Bogdanov and Jonas Natala. So please do check out all of those. Now, first, I want to remind you of the results. The results that we got for the two pulsars published from NICER observations. So we started with a solitary pulsar, J0030, rotating at about 200 hertz. The fact that this is not in a binary means that we lack additional information about, say, the mass or the observer inclination. But luckily, this is a bright enough X-ray emitting pulsar that we were able nonetheless to get pretty decent results on the radius and mass. As you see, at 1 standard deviation, we're getting a radius of about 13 kilometers plus or minus 1, and a mass of about 1.44 plus or minus a 10% uncertainty. The pulsar that we analyzed last year was one that Thankful highlighted in her presentation. This is the pulsar with the heaviest precisely known mass in the skies, at least currently. It rotates faster. The mass, which we obtained thanks to Thankful's leadership and work, is about 2.1 solar masses. And the radius from our analysis, and I'll describe more details later, is about 12 to 16 kilometers. Those of you who work on neutron stars may look at that 16 kilometers and say, whoa, dude, that is one enormous neutron star. So let me try to explain our philosophy here. Our philosophy is that when we are fitting the NICER data, we allow the radius to be anything it needs to be to fit that data. And that can be large radii, 16 kilometers, 20 kilometers, whatever. However, when it comes down to thinking about the implications for the dense matter in the cores of neutron stars, then we bring in other considerations. For example, priors from nuclear physics, or some of the tidal deformability measurements that Jocelyn mentioned yesterday. And this means that those high radii are not in fact favored. Going back now to radii and why radii are important. We see here on the right a figure from the Demarest et al. Paper that also made an appearance in Thankful's presentation. This, as she said, was the first time that we had strong evidence for a neutron star around 2 solar masses. And as we know, if you have an equation of state and you want it to be viable, it has to be able to reach at least the highest precisely measured mass in the pulsar sample. But as you can see from this diagram, have various mass and radius for different equations of state, if you look just at the ones that poke above that red line and therefore satisfy the mass constraint, there's a huge range of radii. It has therefore been known for a long time that a precise and reliable measurement of the radius would provide tremendous leverage in our understanding. However, it's very difficult to measure. As Thankful was describing, the mass, well, it has an effect at a distance. It's called gravity. As a result, that gravity can have an influence on the propagation of signals and the companion and so on. And therefore, given the right circumstances, you can get precise mass measurements. The radius is a different story. The radius does not have effects at a distance. And therefore, you need to use modeling. And the problem is that a lot of the pre-NICER X-ray based measurements of the radius were at least potentially susceptible to huge systematic error. For example, some of the measurements through X-ray bursts or quiescent low mass X-ray binaries, if you got the wrong composition, you could be off by 50%, and yet the fit would be just as good. You couldn't tell any problem. And in the next slide, I'll give you an additional example of how this can be an issue. And as I will explain later, NICER X-ray pulse modeling can help. The example of how it is that you can fool yourself, this is something synthetic. I generated the data myself. I imagined that we had a thermonuclear X-ray burst with 30,000 counts, which is about typical for these sorts of events. And I generated the data with a star that had a radius of 12 kilometers and with a black body emission, but a temperature that varies smoothly from KT equals 2 keV, or about 2 times 10 to the 7 Kelvin at the equator, to 0.2 keV at the pole. Big range in temperatures. But I fit it using a single temperature model, effectively assuming that the entire surface emits uniformly. You might have imagined, given this factor of 10 range in temperature, that a single temperature fit would be terrible, but it is not. As you can see in the plot, the chi-square per degree of freedom is fine. No red flags. You'd have no indication that this is a problem. Also, in this fit, we get a great measurement of the radius, 10.45 plus or minus 0.14 kilometers. The nuclear physicists would be drooling over such a precise measurement, except for the fact it's 10 sigma low. This is the issue. With this type of data, it is possible to have what appears to be a statistically excellent fit and actually be tremendously biased. Now, the variation in temperature. Sometimes you'll hear the statement that, well, if you have that, you'll see pulsations and you'll know there's a problem. Two things about that. One is that if you look at thermonuclear X-ray bursts, you often do see pulsations. Also, if you have axis symmetry, you don't have any pulsations, even if there's a very large latitudinal variation in temperature. That, therefore, is an issue. There are some approaches which have been taken to try to mitigate these issues, and one of the most promising is allowing the emitting area to vary. And for that, I refer you to Jonas Natala's talk later today. But what about NICER itself? Why is it that we have cautious optimism that we have reliability as well as precision in the measurements? And the answer is that, especially in collaboration with Fred Lamb and our various collaborators, we've done a lot of work which suggests that when we fit the type of data that NICER is affording us, systematic errors are minimized. The key here is that NICER, which has a tremendous pulse, a time resolution, it can indicate the arrival time of photons to within 100 nanoseconds, orders of magnitude shorter than the rotational periods. You therefore can get rotational phase dependent spectra, not just the spectra fluxes and distances characteristic of bursts and QLMXPs. So we have done a lot of tests. We generate synthetic data, so we know what the answer is, and we can use models of the synthetic data, which when we fit them, we're fitting them with different models. Maybe we generate oval spots and fit them with circles. We generate spots which have varying temperatures and we fit them with uniform temperature spots, the whole thing. And the general idea of pulse profile modeling was discussed by Serena yesterday, and the codes have been tested extensively. On that conclusion, at least of the systematic deviations we've explored, is that if there is a statistically good fit, there is no significant bias. So that's why we move along cautiously but optimistically to feel that the NICER results are reliable. The types of spot models that we have used are, we try a sort of a simplified approach where we allow the data to tell us what we need to fit. We have tried between 2 and 4 spots. The spots can be oval or circular. They radiate with a uniform effective temperature, but the spots don't have to be linked to each other. They can be anywhere on the surface and they can overlap. You can have no overlap between spots. You can have one spot on top of another. You can have 3 spots on top of each other, whatever it is. We just let the data dictate what the necessary configuration is. And then there's the question of background, which Serena also discussed yesterday. As was pointed out, if we have what we consider to be reliable information about a source of X-rays, which is not the spots, then we can put that into our calculation as a prior on the background. However, even in those cases, we can't be guaranteed that we know all of the non-spot contributions. And in some cases, like our initial analyses of J0030, we did not put in any information. So this answers one of the questions after Serena's talk. If we have no information about the background that we consider reliable, not a problem. We simply allow the background to vary independently, channel by channel, and phase independent. And that way we are conservative in our fit. It may degrade precision a bit, but it means that we're not being misled. Here is a slide which shows you the results of two different fits for the first isolated pulsar. On the left, we have a fit that has two oval spots. On the right, we have an independent fit that has three oval spots. And you can see that these are pretty much on top of each other, which is a good thing. It tends to support the idea that if you have a good statistical fit, and both of these are, then you have reliability. You're not getting radically different mass radius ovals. In terms of the quality of the fit, there are a variety of ways to explore this. Serena mentioned, for example, residuals, which is what we're showing in this plot, which is a bit reminiscent of TV test patterns for people who remember back that far. On the vertical axis, we have the energy channel from NiSER. And on the horizontal axis, we have the rotational phase bin, where we have 32 phases. The gray scale indicates chi, the signed square root of chi square. And the thing you are looking for here, are there any patterns? Do you tend to have substantial residuals of one sign or another in particular channel or phase groupings? And the answer is no. There's no evident pattern. Also, you can look at traditional measures of goodness of fit, such as chi square, and it's fine. So this is no problem at all. And therefore, we think that this is going to give us reliable answers. That was the first of the two pulsars that we reported from our NiSER analysis. The second one is the heavy one, as we heard about from Thankful. And this one needs a little help from its friends. That's because this is 20 times fainter in the X-rays than the first pulsar we mentioned. It is of tremendous interest due to its high mass, and therefore we threw everything we could at it. Not only did we use the excellent information about mass and observer inclination and, of course, distance that was obtained by people like Thankful and Emanuel Fonseca, but we also added information from the European Space Agency's XMM Newton mission. All this came together, and what we ended up with is a radius that at 1 sigma goes from about 12 to 16 kilometers, where, remember, we don't restrict the radius range in this case. Again, the fit is good. You can see we've discovered color in this case. Apparently, when we got to this heavy pulsar, we went into Oz. And once more, we see no evident pattern in the residual. The chi-square is excellent for the entire data set. It's good for the bolometric NiSER data. It's good for the XMM data, and so on. So once more, we look at this and we say, yeah, maybe we've got some reliable information about the radius of this star as well. Serena also mentioned the advances that we are now making in a variety of ways within NiSER. In particular, she mentioned the inclusion of background with the so-called 3C50 data set, which has been led by Ron Remillard. Now, that data set actually is far more updated than the one that we used for our publications last year. However, it also involves much stricter cuts, really looking for the highest quality data, so that in fact, the total exposure is slightly less than it was last year. On the right, we have a figure which compares our results from the published information in 2021. And when we use NiSER alone, NiSER plus XMM, when we use the data set by itself, but no background constraints, and then when we do add background. So all of this is coming together. Now, what you see on the top is that when we use only the NICER data from the 2021 publication, we have something which is peaked at a moderately low radius. When we add the 3C50 data set, which has much cleaner data, probably better determined harmonics, then it moves up to a broader and peaked at a higher radius. Then when you add the background, it moves to an even slightly larger radius. As Serena explained, if you know that some of the counts are background, that means that the remaining counts from the spots are modulated more strongly, and this tends to point towards larger radii. And the bottom plot, you see NICER and XMM, where we see that things are actually much closer to what we had, essentially because the XMM observation tells us the emission from the pulsar itself, and therefore, in some sense, implicitly, you already have the background. Net result is that there are some updates, but we agree with Serena that there are no major equation of state implications, at least with these data. Now, I'd like to talk about what we believe we have learned about the equation of state of the dense matter and neutron star cores from these observations and others. And this is something which is obviously of great interest to many people. It's one of the major aspects of excitement about NICER. Since this is my major plot, I'm going to spend a considerable amount of time walking you through what we have here. We see 4 panels in the plot. And to explain what's going on, note that the normal thing that is done, that we also do, is to assume that we actually know the equation of state up to some threshold density. The threshold density we choose is half of nuclear saturation, because this is roughly the boundary between the crust and the core. We choose as our known equation of state up to that density, the QHC19 equation of state from Boehm et al. But note that if we were to choose other popular examples such as SLY4 or whatever, we'd get basically the same answer. So this is the reason why at the left end of each of these diagrams, we go to a point, because at that point we claim we know what's going on. However, if we think about going to higher density, we need some framework to extend the equation of state. There is no definite framework to do this. We don't know the answer, so we tried 3 different types. On the top left, we use a piecewise polytrope, which is a popular choice of long standing. Top right is a spectral equation of state, which has been used by the LIGO and Virgo teams. Bottom left, Gaussian processes, which have been used in many problems and were pioneered in this context by Philip Landry and Reed Essick. And then the bottom right, we have a summary, and I'll explore that a bit more in the next slide. For a given line type, the bottom part is the 5th percentile of the pressure at a given number density, and the upper curve is the 95th percentile. And finally, if you look at the different line types, the dotted ones are the priors, just whatever we started with. Moving up then, the dot dash adds the pre-NICER information. So this is not only the equation of state, the prior, but also things like the symmetry energy, the high masses that Thankful and others are measuring, the tidal deformability from 1708-17. And then we go into the dashed line, we add the first pulsar from NICER, and then finally the solid line, the second. So this tries to represent in a somewhat information dense way what's happening when you're putting everything together using different ways of extending your equation of state to high density. This is an expansion of the bottom right portion where we see everything together. And here are our 3 equation of state models, the Gaussian processes, spectral, and piecewise polytrope. And what we find is that there's good equation of state convergence in roughly the 1.5 to 5 nuclear saturation density range. Please also see the talk on Thursday by Geert Rijmakers, who is going to discuss some of his group's work on this. Now, it's not perfect. You can see that obviously there's still some dependence on the framework that you have, but if we go back, look at the extreme breadth of the priors compared to what we have now. We are data dominated at this stage. You can also look at this in terms of what we've done in terms of the tight mass radius constraints. Again, we have a sequence. Here we are focusing on the Gaussian processes framework, but you get similar results for the other frameworks. In the top left, we start out with our prior. Here, as in the other panels, we have the mass on the vertical axis and the radius on the horizontal axis. And at a given mass, the left edge of the pink region is the 5th percentile of the radius at that mass, and the right edge is 95%. Then the blue goes from 25 to 95. In the top right, we add the pre-Neisser observations. Again, things like the symmetry energy, the high masses, the tidal deformability. Bottom left, we add our first pulsar, and bottom right, finally, our second pulsar. This is cumulative. Everything is increasing the information. Looking at the top right and bottom right figures, we see what a huge difference the Neisser observations have made. What we find, in fact, is that if we use all three equation of state models, the piecewise polytrope, Gaussian processes, and spectral, at a canonical 1.4 solar mass neutron star, the radius we find is between 11.8 and 13.1 kilometers. Now, of course, depending on exactly how you do this, it can be extended a bit more than that, but it's basically plus or minus 5%. This is rather impressive. It's a real testament to the work of everybody in the field, not just the Neisser people, but the radio observers, the people who have done the gravitational wave analyses, to be able to go in basically a decade from throwing our hands up, not knowing what we can say astronomically, to having some remarkably tight constraints. What then is going to come in the future? Both of the groups within Neisser are working on an update to the analysis of the heavy pulsar. We have about 60% more Neisser data. Now, in addition to that, there will be an intermediate paper published, which gives the results for the 3C50 data set and shows how to put in some of the background. This is something which we expect to result in a 20 to 30% reduction in the uncertainty on the radius. So going from, at least in our measurement, 12 to 16 kilometers to something that could be a delta of 3 kilometers or 3.5 kilometers. Basically, it's something that could be improved rather substantially. In addition, as Serena also mentioned, there are other pulsars. One of the most anticipated ones is J0437, because it is the brightest X-ray emitting pulsar of this class, the non-accreting class. It also has a known mass of about 1.4 solar masses. This will therefore help cross-check our published results. Are we getting similar masses? Are we getting different masses? Well, I'll leave you in suspense, and you'll have to read the papers when they come out. I'm pleased to tell you, as many of you probably know, that NASA has granted Neisser a 3-year extension. So within that time, there will be tremendous improvement in the data. Also, as Serena noted, there are 3 different groups within Neisser working on background models. This means that we're going to have more and more reliable information to put in, which should improve the precision and reliability of our data. So in conclusion, for the 2 published pulsars, the heavy one, 12 to 16 kilometers, the lighter one or ordinary one, 12 to 14. And something that is very exciting to me is that we are now data dominated between about 1.5 and 5 times nuclear saturation density. And we know the radius of a canonical pulsar to about 5%. Stay tuned. The best is yet to come. Thank you, and I'll be happy to take questions.